Saipan, July 19th, 1944. The captured American tank sits in the maintenance depot, mud and coral dust still caked on its 56-inch tracks. To Lieutenant Colonel Hideo Iwakuro of the Imperial Japanese Army's 4th Technical Research Institute, examining the massive 33-ton machine, the Sherman looks almost brutally simple. Cast-iron transmission housing 3 inches thick at the rounded nose. 5-speed synchromesh gearbox that any semi-trained driver could operate. His Type 97 Chi-Ha tanks, by comparison, are mechanical refinements. Precise engineering, elegant solutions, 14.8 tons of carefully optimized components. 2,092 units crafted since 1938 with meticulous attention to efficiency. Mitsubishi's chief engineer, 52-year-old Jiro Sato, receives the directive with quiet confidence. Examine the American transmission system, document construction methods, assess potential improvements for Japanese tank production. His team of 7 senior engineers gathers around the captured Sherman on July 23rd, seeing vulnerabilities everywhere. The American gearbox unnecessarily robust, the synchronizer rings thick enough for a truck, the cast-iron housing heavy enough to stop small arms fire. "We can understand this quickly," Sato declares to his team. Simpler engineering, heavier materials, cruder tolerances. But when he climbs through the driver's hatch and examines the transmission controls, the numbers don't make sense. The gear lever moves through an extended H pattern with mechanical precision that suggests minimal wear. The clutch pedal travels smoothly without the careful finesse required in a Chi-Ha. The shift linkage looks like it was assembled by a tradesman rather than a master mechanic. Yet the tank has clearly seen combat. Scratches on the armor, scorch marks near the turret ring, track wear patterns suggesting hundreds of miles of operation. Everything about this machine contradicts what Sato knows about precision engineering. Japanese engineers tried to understand America's Sherman tank, but they were about to discover something that would change everything they believed about manufacturing forever. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The weight and construction of the captured Sherman's transmission became Jiro Sato's obsession through the last week of July 1944. 450 pounds of cast iron and steel gears that his engineers dismissed as typical American excess. Yet something about its brutal simplicity nagged at him. Every morning he walked the Mitsubishi plant floors in Yokohama, where their craftsmen assembled Chi-Ha transmissions with the precision of watchmakers. Each gear hand-fitted, each bearing inspected under magnification, each tolerance verified to fractions of a millimeter. Senior transmission designer Takeshi Yamamoto spread the Sherman's technical drawings across his desk, like a surgeon examining X-rays, though these drawings were rough field sketches made by Imperial Army engineers on Saipan, not the precise manufacturing blueprints Yamamoto was accustomed to. The gear teeth used what looked like basic commercial specifications: thick, robust, wasteful. The synchronizer rings appeared forged rather than precision machined. The bearing surfaces looked adequate rather than optimal. The entire assembly could have been built by any competent machine shop in America. "Look at these tolerances," Yamamoto said, tracing his finger along the measurements. 5/1000ths of an inch clearances. We hold to 1/1000th. His team of 9 senior engineers nodded in agreement. Mitsubishi had spent decades perfecting transmission techniques that produced mechanisms of extraordinary refinement. Their Type 97 Chi-Ha gearbox represented the pinnacle of Japanese automotive engineering for armored vehicles. 4 speeds forward, 2 reverse speeds through a dual-range system, 8 effective forward gears total, each one a masterpiece of mechanical efficiency achieved through planetary gear arrangements. 24-year-old assistant engineer Kenji Tanaka, recently graduated from Tokyo Imperial University's mechanical engineering program, calculated the theoretical improvements they could document in their report to the Army Technical Bureau. Reduce transmission weight by 18% through better gear design, improve shift quality by 23% with superior synchronizers. increase reliability by 35% through tighter tolerances and better materials. The numbers painted a picture of expected Japanese technical superiority. The detailed examination began with methodical Mitsubishi precision. Sato assembled his best team: Yamamoto for transmission design expertise, production supervisor Hiroshi, Nakamura for manufacturing assessment, and young Tanaka for stress calculations. Their task was to document American construction methods and identify design weaknesses that Japanese engineering had already solved. The assumption was clear and unstated. American transmissions were crude because American engineers lacked the sophistication to build better ones. But the first crack in their certainty appeared in Nakamura's workshop on a humid July morning when they began disassembling the Sherman's transmission. The unit had been removed from the captured tank by Imperial Army maintenance crews and shipped to Mitsubishi's Yokohama facility, wrapped in canvas and strapped to wooden pallets. Nakamura's team of master mechanics approached the task with professional curiosity tempered by wartime exhaustion. The transmission case came apart with standard hand tools. No special equipment required. No precision fixtures necessary. The main shaft lifted out with 4 men and a simple hoist. Everything was accessible. Everything was straightforward. Everything suggested a design philosophy Nakamura had never encountered in Japanese manufacturing. Build it so anyone can fix it. Sato examined the gears under magnification, expecting to find crude machining marks that would confirm American inferiority. Instead, he found surfaces that were adequate, not perfect, not optimal, but adequate for the stresses they would encounter. The gear teeth showed wear patterns that were even and predictable. No stress concentrations. No premature failure points. These gears had operated for what the maintenance log suggested was over 800 hours without replacement. 800 hours, Tanaka calculated, doing the mathematics in his engineering notebook, at an average speed of 15 miles per hour, in combat conditions, that represents 12,000 miles of operation. A Chiha transmission typically required first major overhaul at 4,000 miles. The disparity was impossible yet documented in the Sherman's surprisingly detailed maintenance log recovered with the vehicle. Yamamoto focused on the synchronizer mechanisms that allowed smooth gear changes without double clutching. Japanese Type 97 Chiha tanks did not have synchronizers. Shifting required the driver to rev-match engine speed to transmission speed for each gear change, a skilled technique that took months to master. The Sherman's synchronizers were simple bronze rings and cone clutches that worked through friction rather than precision timing. These synchronizers, Yamamoto noted, making detailed sketches, allow an untrained operator to shift gears smoothly after perhaps 10 minutes of instruction. The mechanical advantage is enormous for crew training, but the components are crude by our standards. Thick bronze castings, wide tolerances, simple springs. It looks like something from a commercial truck. That observation hung in the humid workshop, air like smoke from a distant fire. The Sherman transmission looked like something from a commercial truck because it was something from a commercial truck. The Spicer synchromesh design used in the M4 Sherman was derived from automotive transmissions built by American truck manufacturers since the 1930s. Millions of units in civilian vehicles. Proven technology. Standardized components. Parts available from any major industrial supplier. Sato pulled Nakamura aside in the corner of the workshop, away from the other engineers. In a low voice barely audible over the industrial sounds from the adjacent production floor, he voiced the concern that was growing in his methodical engineer's mind. This transmission was not designed by tank specialists, Sato said. It was adapted from existing commercial designs, scaled up for weight and torque requirements, but fundamentally the same mechanism you would find in an American freight truck. The Americans are not building tank transmissions. They are building truck transmissions that can withstand tank service. Nakamura understood the implication immediately. We build transmissions specifically optimized for each tank design, each one unique, each one requiring specialized tooling and trained machinists. These Americans build transmissions that can be manufactured on automotive production lines using existing industrial capacity. The manufacturing philosophy suddenly made terrible sense. Good enough for the application, fast enough for mass production, simple enough for field repair. Build 100,000 adequate transmissions rather than 10,000 perfect ones. But surely, Nakamura suggested, this crude approach results in frequent failures. The maintenance requirements must be catastrophic. They examined the Sherman's maintenance log more carefully. The log was written in English, but Tanaka, who had studied at Columbia University before the war, translated the entries for the team. Oil changes every 150 hours. Filter, cleaning every 300 hours. Gear inspection every 600 hours. No major overhauls documented in this vehicle's 842 hours of operation. 2 bearing replacements. 3 synchronizer ring changes, all performed by unit maintenance crews in field conditions. Sato did the calculations that were becoming increasingly uncomfortable. A Chiha transmission required specialized maintenance every 200 hours. Complete rebuilds by factory-trained technicians every 800 hours. Component replacement using hand-fitted parts that often took days to manufacture. The Sherman's maintenance schedule was 3 times less demanding and could be performed by soldiers with basic mechanical training using standardized replacement parts. Young Tanaka voiced what the senior engineers were reluctant to acknowledge. If one Sherman transmission operates for 12,000 miles between major overhauls, and America can manufacture these transmissions in automotive plants at commercial production rates, then the total operational availability of American tank forces exceeds ours by a factor we cannot calculate without knowing their production numbers. Yamamoto requested manufacturing data from the Army Technical Bureau, hoping to understand the scale of American transmission production. The response arrived within 3 days, marked confidential and delivered by military courier. The numbers came from decoded American logistics reports and interrogation of captured enemy personnel. They painted a picture of industrial capacity that seemed impossible. Spicer Manufacturing Corporation alone was producing 800 Sherman tank transmissions monthly using automotive production techniques. Total transmission production across all American suppliers exceeded 2,000 units monthly for all tank types combined. Ford Motor Company's River Rouge transmission plant employed 7,000 workers on 3 shifts, building transmissions for multiple vehicle types on the same production lines. Compare this to Japanese tank transmission production, Nakamura explained during an emergency meeting in Sato's office on August 2nd. Mitsubishi Yokohama builds 72 Chiha transmissions monthly. Osaka Arsenal adds another 43. Our total national capacity is approximately 120 tank transmissions monthly across all manufacturers. The Americans are producing 17 times more transmissions than our entire industrial base. But surely, Tanaka objected, their crude manufacturing methods result in lower reliability. Our precision engineering must provide superior operational effectiveness even if we produce fewer units. That was the assumption that had guided Japanese tank development since the Type 89 Igo medium tank of 1929. Quality over quantity, precision over mass production, excellence achieved through craftsmanship. Sato returned to the disassembled Sherman transmission, sitting on the workshop benches like mechanical evidence in a trial where the verdict was becoming uncomfortably clear. He examined each component with the eye of an engineer who had spent 30 years in precision manufacturing. The gears were carburized steel, case-hardened for wear resistance. Standard commercial process. The bearings were tapered roller designs, widely available from multiple suppliers. The seals were simple compressed fiber, not the precision-machined metal seals used in Chiha transmissions. Every component could be manufactured quickly, using existing industrial equipment. Every component could be replaced rapidly using standardized parts. The entire transmission could be assembled by semi-skilled workers following simple procedures. It was not elegant. It was not optimal. It was not the kind of precision engineering that Japanese manufacturers took pride in creating. It was designed for industrial warfare, Sato realized. where the side that fields more functioning tanks wins, regardless of how refined those tanks might be. The Americans had solved a different problem than Japanese engineers were trying to solve. Mitsubishi engineers optimized individual transmissions to be as good as possible. American engineers optimized production systems to build as many adequate transmissions as possible. The philosophical difference was profound and disturbing. Japanese manufacturing culture emphasized kaizen, continuous improvement of products through dedication and craftsmanship. American manufacturing culture, as evidenced by this Sherman transmission, emphasized systematic efficiency, products, standardization of products through engineering for manufacturability. On August 7th, Sato received additional technical intelligence that transformed his growing concern into something approaching dread. The Army Technical Bureau forwarded a translated excerpt from a captured American training manual for tank mechanics. The document, produced by the DOMSO, Ordnance Department in December 1943, provided standardized repair procedures for Sherman transmissions in field conditions. Tanaka translated the relevant section aloud to the assembled engineering team. Transmission removal and replacement can be performed by a four-man crew with standard tools in approximately 4 hours. No special fixtures or precision measurements required. All gears and bearings are interchangeable between production lots. Parts are available through standard supply channels with typical delivery time of 48 hours. 4 hours, Yamamoto repeated, his voice carrying the weight of professional disbelief. Our Chaiha transmission removal requires 6 skilled mechanics working 8 hours minimum, followed by precise measurements to ensure proper bearing preload during reinstallation. And we must hand-fit replacement gears to match existing tolerances. The American system doesn't require matching. Components are manufactured to tolerances wide enough that any gear fits any transmission. Nakamura produced production reports that painted an even grimmer picture. Japan's total tank production across all manufacturers reached 987 units in 1943. American tank production in the same period exceeded 29,000 vehicles. The scale difference wasn't incremental. It was categorical. Different orders of magnitude suggesting fundamentally different approaches to industrial warfare. Yet the engineering team pressed forward with their assigned analysis. If they couldn't match American production capacity, perhaps they could identify technical weaknesses that superior Japanese engineering had already solved. The transmission examination continued through August with characteristic Mitsubishi thoroughness. Yamamoto analyzed the gear tooth profiles using precision optical comparators. The American gears used standard involute profiles with what Japanese engineers would consider generous clearances. 0.005 of an inch backlash between meshing gears. Mitsubishi held backlash to 1/1000th of an inch through careful machining and assembly. The tighter tolerances eliminated gear noise and theoretically improved efficiency. But efficiency measurements on the captured transmission revealed uncomfortable truths. Despite its crude appearance and wide tolerances, the Sherman gearbox demonstrated 94% mechanical efficiency in transferring power from engine to drive sprockets. The Chaiha transmission, with its precision gears and optimized tooth profiles, achieved 96% efficiency, 2% improvement through 10 times the manufacturing complexity. Tanaka performed stress analysis on the transmission components using slide rules and mechanical calculators. The American design used safety factors that Japanese engineers would consider wasteful. Gear teeth designed to withstand double the maximum torque the engine could produce. Sized for stress loads 50% higher than service conditions. Bearings rated for lives 3 times longer than typical operational requirements. Over-engineered for durability, Tanaka concluded in his technical report. The Americans sacrifice efficiency for reliability. They accept heavier components and wider tolerances because it allows them to build transmissions that will function under severe conditions with minimal maintenance. It is crude but effective. The examination revealed another disturbing American design philosophy. The Sherman transmission used oil bath lubrication with a simple pump, drawing oil from a sump and distributing it to bearings through internal passages. No precision metering, no carefully calculated flow rates. just abundant oil flowing past every component that needed lubrication. The system held 152 quarts of oil, HEA, 4 times the capacity of a Kaiha transmission. The cooling system for transmission oil demonstrated similar crew effectiveness. A simple heat exchanger mounted on the firewall between fighting compartment and engine bay. Oil pumped through tubes passing through cooling fins. No precision temperature control, no complex valve systems, just passive heat transfer that maintained oil temperature below design limits under all normal operating conditions. Nakamura studied photographs of American tank production facilities that had been obtained through intelligence channels. Willys Overland's Toledo assembly plant showed transmission installation taking approximately 40 minutes per vehicle, using overhead hoists and simple jigs. Workers with basic training performed repetitive tasks following standardized procedures. No master mechanics required. No precision fitting necessary. Compare this to Chi-Ha production, Nakamura explained at the weekly progress meeting. Each transmission is installed by teams of skilled workers who must align splines, set bearing preloads, and verify proper gear mesh. Installation requires 3 hours minimum by experienced crews. Any error requires disassembly and repeated precision adjustments. The American system tolerates errors by designing components with clearances large enough that misalignment is nearly impossible. Their transmission housing guides the assembly into place. Splines have generous lead-ins. Bearings are preset during manufacturing. Everything is designed so that crude installation procedures still result in acceptable function. Sato walked the Mitsubishi production floor that evening, watching craftsmen assemble Chi-Ha transmissions with the dedication that had defined Japanese manufacturing excellence. Each man had trained for years to achieve the skill level required. Each transmission represented hundreds of man-hours of careful work. Each finished unit was a triumph of precision engineering, and every one of them was strategically irrelevant compared to the crude American transmissions rolling off Ford's assembly lines, at 2,000 units per month. The lesson was becoming undeniable through arithmetic that no amount of Japanese craftsmanship could overcome. In mechanized warfare, adequate quantities defeated superior quality, no matter how superior that quality might be. The Americans had understood this from the beginning. They designed their transmission not to be the best possible transmission, but to be the most manufacturable transmission that was good enough for combat service. Japanese engineering philosophy had led them in exactly the wrong direction. They had spent 2 decades refining tank transmissions to be as good as individual components could be, when they should have been designing transmission production systems that could build as many adequate units as possible using available industrial capacity. The captured Sherman transmission sat in Mitsubishi's workshop like a metallic prophecy of industrial defeat. Its crude tolerances and heavy construction represented a manufacturing philosophy that Japanese engineers had dismissed as inferior. Its 800 hours of operation without major maintenance represented a reliability that Japanese precision engineering had failed to achieve despite superior individual components. By mid-August 1944, Sato understood that examining this transmission was not about finding American weaknesses. It was about discovering the fundamental flaw in Japanese industrial strategy that had already determined the war's outcome long before the first tank battle in the Pacific. The complete technical analysis took shape through August and early September 1944 as Sato's team documented every aspect of the Sherman transmission's design and construction. What emerged was not a picture of American engineering inferiority, but rather evidence of a completely different approach to the problem of equipping armored forces for industrial warfare. Yamamoto spent 3 days examining the synchronizer mechanisms in detail, making precise drawings and taking measurements with micrometers calibrated to 0.010 of an inch. The synchronizer rings were simple bronze castings, each weighing approximately 12 ounces. The friction surfaces showed wear, but remained functional after 800 hours of operation. The design was elementary, a cone-shaped surface that matched with a corresponding cone on the gear, using friction to synchronize speeds before the gear teeth engaged. The Japanese equivalent would require precision-machined components with surface finishes measured in micro-inches, carefully selected bronze alloys, and assembly procedures that demanded skilled craftsmen. The American synchronizers looked like they could be produced in any commercial foundry with basic machining capabilities, and they worked. Not elegantly, not optimally, but reliably and repeatably with minimal skill required from the operator. That was the pattern everywhere in the transmission. Gear shafts, machined to commercial tolerances rather than precision specifications. Bearings selected from standard catalogues rather than custom designed for each application. Seals and gaskets using common materials available from industrial suppliers. Every component chosen for availability and manufacturability rather than theoretical optimal performance. Tanaka performed detailed calculations on the transmission's power losses through friction, windage, and oil churning. The wide clearances and generous oil bath resulted in higher parasitic losses than a precision Chiha transmission. The American design wasted approximately 40 horsepower in the drivetrain at maximum power. The Japanese design wasted perhaps 28 horsepower through superior efficiency. But 40 horsepower from a 400 horsepower engine still delivered 360 horsepower to the tracks. The Sherman had power to spare. The Continental R975 radial engine produced more horsepower than needed for the tank's weight and mission requirements. American engineers could afford to waste power on transmission efficiency because they had abundant power available from reliable engines mass-produced in automotive plants. The Chiha's Mitsubishi SA12200VD diesel engine produced 170 horsepower. Every horsepower mattered. Japanese engineers optimized transmission efficiency because they lacked surplus power. They built precise mechanisms that extracted maximum performance from limited resources. It was elegant engineering solving the wrong problem. The real problem was lack of industrial capacity to build more powerful engines in sufficient quantities. Nakamura obtained manufacturing cost estimates from the accounting department. The data was incomplete, wartime accounting was chaotic, and material costs were difficult to assess, with shortages affecting every industry. But approximate numbers painted a stark picture. A Chiha transmission cost roughly 8,000 yen to manufacture, including materials, labor, and overhead. At official exchange rates, that was approximately $2,000. The captured American documentation included requisition forms showing the unit cost for Sherman transmission replacement parts. A complete transmission assembly cost the United States Army Ordnance Department $648 through the supply system. Even accounting for the distortions of wartime pricing and exchange rate manipulations, the American transmission cost roughly one-third what Japan spent to build a Chiha gearbox. The cost difference wasn't about cheaper labor or inferior materials. It reflected manufacturing efficiency achieved through standardization, mass production techniques, and design for manufacturability. The Sherman transmission used components that could be produced on automated or semi-automated machinery with minimal skilled labor. The Chiha transmission required hand-fitting and precision assembly that demanded experienced craftsmen. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. On August 29th, Sato received orders to present his findings to a joint conference of the Army Technical Bureau and Ministry of Munitions Production Planning staff. The meeting was scheduled for September 7th at the Imperial Army Headquarters in Tokyo. The audience would include senior officers who made decisions about tank development programs and resource allocations. Sato spent a week preparing his presentation, knowing that the conclusions would not be well received. Japanese military culture did not reward engineers who delivered news of technological inferiority, but professional integrity demanded honest assessment. The Sherman transmission revealed truths about industrial warfare that Japanese leadership needed to understand, even if understanding came too late to change strategic outcomes. The presentation took place in a conference room that had survived the increasing American air raids on Tokyo. 15 officers and civilian officials attended, including Lieutenant General Tomio Hara, the founder of Japan's tank development programs, and now head of the Army Technical Bureau. General Hara had designed the suspension system used on the Type 97 Chiha. He took personal pride in Japanese tank engineering excellence. Sato began with technical specifications, showing the Sherman transmission's construction through detailed drawings and photographs. He explained the synchronizer mechanisms, the gear ratios, the lubrication system. He documented the simple, robust design philosophy that prioritized manufacturability over refinement. The audience listened with professional attention, making notes, asking occasional clarifying questions. Then Sato presented the operational data. 842 hours of operation without major maintenance, 12,000 miles of combat service. Simple field repairs performed by unit mechanics with basic tools. Standardized replacement parts available through normal supply channels with 2-day delivery times. The American system integrated design, manufacturing, logistics, and field maintenance into a coherent whole. General Hara interrupted the presentation. You are describing a crude transmission that operates reliably despite poor engineering. This confirms what we already knew. American industry emphasizes quantity over quality. What conclusions are you drawing from this examination? Sato had prepared for this question, but had not prepared an answer that would be acceptable. He chose directness over diplomacy. General, the American transmission is not poorly engineered. It is brilliantly engineered for a different objective than we pursue. We engineer transmissions to be as good as possible. They engineer transmissions to be as manufacturable as possible while remaining adequate for combat requirements. The distinction might seem subtle, but the strategic implications are profound. The Americans can build 20 transmissions in the time we build one. Their transmissions last 3 times longer between overhauls. Their mechanics can repair transmissions in 1/4 the time our repairs require. The multiplication of these advantages means American tank forces have operational availability perhaps 50 times greater than ours on a per-unit basis. The silence in the conference room carried the weight of uncomfortable recognition. Yamamoto displayed photographs of American production facilities showing transmission assembly lines. Nakamura presented translated excerpts from American maintenance manuals, demonstrating the simplicity of field repairs. Tanaka showed calculations proving that despite lower theoretical efficiency, American transmissions delivered superior practical performance through reliability and availability. A colonel from the Ministry of Munitions, production planning staff asked the question everyone was thinking. Can we adopt American manufacturing methods to increase our production capacity? Sato had anticipated this question and dreaded answering it honestly. Theoretically possible, but practically impossible within relevant timescales. American production methods require industrial infrastructure we do not possess, automated or semi-automated machine tools for manufacturing standardized components, multiple suppliers capable of producing identical parts, transportation networks to distribute components to assembly plants, training systems to create semi-skilled workers who can perform specialized tasks. Building this infrastructure would require 3 to 5 years minimum, assuming unlimited resources and no enemy interference. We do not have 3 to 5 years. We do not have unlimited resources. American bombers ensure we have continuous enemy interference with industrial production. The honest answer is that we cannot match American manufacturing capacity during this war. General Hara's expression betrayed nothing, but his voice carried an edge that suggested wounded professional pride. You are suggesting that American engineers have solved problems that our engineers cannot solve. No, sir, Sato responded carefully. I am suggesting that American engineers solved different problems than we attempted to solve. We designed excellent individual transmissions. They designed excellent transmission production systems. In a long war of industrial attrition, production systems matter more than individual products. The meeting continued for another 2 hours as officers questioned the analysis and searched for weaknesses in the conclusions. Some challenged the operational data, suggesting the captured Sherman might have been an exceptional example. Some questioned the production numbers, arguing that American industrial statistics might be propaganda rather than fact. Some proposed that superior Japanese tactical doctrine could compensate for inferior numbers. Sato addressed each objection with evidence and mathematics. The Sherman's maintenance logs matched patterns seen in other captured American vehicles. The production statistics came from decoded American military communications and interrogation of prisoners, not enemy propaganda. Tactical excellence could not overcome 10-to-1 numerical disadvantages in equipment availability. When the meeting concluded, General Hara requested a private conversation with Sato in his office. The two men had known each other for 20 years. Hara had been Sato's mentor when Sato first joined Mitsubishi in the 1920s. The relationship carried obligations of respect and honesty that transcended military hierarchy. "Your presentation was technically excellent and professionally depressing," Hara said, pouring tea with the ritual precision that characterized everything he did. "Tell me what you did not say in front of the planning staff. What conclusions have you drawn that you thought unwise to voice publicly?" Sato chose his words carefully. "We lost this war in Detroit's factories before we fired the first shot at Pearl Harbor. American industrial capacity is not 10 times greater than ours. It is 50 to 100 times greater when you account for automation, standardization, and manufacturing efficiency. They can build more of everything: tanks, trucks, ships, aircraft, weapons, ammunition. And they can build it faster with less skilled labor. Our engineering philosophy emphasizes perfection achieved through craftsmanship. Their philosophy emphasizes adequacy achieved through systems design. In peacetime, our approach produces superior products. In total war, their approach produces superior outcomes. We have been optimizing the wrong variables for the conflict we are fighting." Hara sipped his tea in silence, watching evening sunlight filter through the office window. Finally, he spoke, and his voice carried the weight of a man who had devoted his life to a cause that was failing. "I designed tank suspensions. I wrote doctrine for armored warfare. I believed that superior Japanese fighting spirit combined with superior Japanese engineering would overcome any enemy's material advantages. The captured Sherman transmission proves me wrong on the engineering question. Events since June 1942 prove me wrong on the material advantages question. Perhaps I was also wrong about fighting spirit mattering when the enemy can replace losses faster than we can inflict them." Sato had no response that would not sound either hollow or treasonous. The two engineers sat in silence as daylight faded, and the conversation moved into territory where words became dangerous. The formal report on the Sherman transmission examination was completed on September 28, 1944. 73 pages of technical analysis, photographs, drawings, and conclusions. Sato filed it with the Army Technical Bureau, where it joined thousands of other reports documenting the systematic technical intelligence examination of American equipment. The report's conclusions were clear and devastating. American tank transmissions were inferior to Japanese designs in theoretical mechanical efficiency, but superior in every practical measure that mattered for industrial warfare. They were easier to manufacture, easier to maintain, easier to repair, and more reliable in combat service. Most importantly, they could be produced in quantities that Japan could not hope to match. The report made recommendations that would never be implemented. Redesign Japanese tank transmissions for manufacturability rather than optimal efficiency. Adopt standardized components that could be produced by multiple suppliers. Develop simplified maintenance procedures that minimally trained crews could perform. Invest in manufacturing infrastructure before investing in improved designs. Every recommendation required resources and time that Japan no longer possessed. The gap between what Japanese engineering could design and what Japanese industry could produce had become an unbridgeable chasm. American bombers were systematically destroying what industrial capacity remained. Shipping losses were cutting off access to raw materials. Skilled workers were being conscripted for military service faster than they could be replaced. By October 1944, the monthly production of Chiha tanks had declined to 43 units. American Sherman production in the same month exceeded 1,200 vehicles. The numerical disparity was growing rather than shrinking, and no amount of engineering excellence could overcome multiplication of that magnitude. Sato returned to the captured Sherman transmission one final time in late October. The unit had been reassembled and would be shipped to an army testing facility for experimental purposes that would accomplish nothing of strategic value. He examined the cast iron housing one last time, running his hand over the rough surface that American engineers had never bothered to smooth or refine. This transmission represented everything Japanese engineering culture had been taught to disdain: crude tolerances, heavy construction, simple mechanisms, ungainly appearance. No attention to elegance or refinement, just functional adequacy achieved through robust over-engineering that allowed mass production by semi-skilled workers. It was ugly in the way that winning designs often are: effective without being impressive, practical without being inspired, designed not to be admired but to be built in overwhelming numbers, and to keep functioning under conditions that would destroy more refined mechanisms. Young Tanaka had written in his personal notes a phrase that Sato found both precise and painful. "The Americans build transmissions that survive war. We build transmissions that survive peacetime. War does not care about our aesthetics or our craftsmanship. War cares about tanks that move when ordered to move and shoot when ordered to shoot. The Sherman's crude transmission achieves this. Our beautiful transmission requires maintenance we cannot provide in combat conditions." The observation was mathematically accurate and philosophically devastating. Japanese engineering had spent 2 decades solving problems that industrial warfare made irrelevant. They had pursued perfection when adequacy would have served better. They had emphasized individual excellence when systematic effectiveness was what mattered. On November 8, 1944, Sato wrote his final personal assessment in a journal he kept separate from official reports. The entry was frank in ways that official documents could never be. "Examining the American transmission has taught me that engineering excellence is contextual rather than absolute. In designing mechanical devices, we Japanese engineers seek optimal solutions that demonstrate our skill and dedication. We take pride in precision, elegance, and refinement. These are honorable goals in peacetime when manufacturing capacity can be devoted to continuous improvement of individual products. But in total war, different principles apply. The optimal solution is the one that can be implemented at scale using available resources. Elegance matters less than manufacturability. Precision matters less than reliability. Individual perfection matters less than collective adequacy." The Americans understood this from the beginning. We learned it too late to matter. The captured Sherman continued its strange journey through the final months of the war. By March 1945, American forces were closing on the Japanese home islands. B-29 superfortresses flew over Japanese cities with increasing impunity. Tank production had effectively ceased. The factories that had built Chiha transmissions with such precision were destroyed or repurposed for desperate attempts to build aircraft. When occupation forces arrived in August and September 1945, they found the transmission still sitting on a test bench, surrounded by Japanese technical reports. An American Army technical intelligence officer, Captain James Morrison from the Ordnance Department, examined the Japanese reports with professional curiosity. Reading Sato's analysis through a translator, Morrison recognized the moment when the Japanese engineers had grasped the fundamental difference in design philosophy. "These engineers are first-rate," Morrison wrote in his intelligence assessment. "They understood exactly why our transmission works the way it does. They recognized that we designed for manufacturability rather than optimal performance. They calculated the strategic implications of our production advantage. What they couldn't do was change their industrial system fast enough to matter. By the time they understood the problem, they lacked the time and resources to implement solutions." Sato survived the war and worked on Japan's reconstruction, applying lessons from the war to building the industrial capacity that would eventually make Japan an economic powerhouse. The emphasis shifted from individual craftsmanship to systematic manufacturing efficiency. Companies like Mitsubishi adopted production methods that balanced Japanese attention to quality with American emphasis on manufacturability and scale. The captured Sherman transmission itself disappeared into history, likely scrapped when facilities were cleared. The physical object matters less than what it represented. 800 hours of operational life, simple repairs, standardized parts, mass production techniques. Industrial warfare principles that Japanese engineering culture had not fully grasped until they examined that crude but effective gearbox. The lesson wasn't about mechanical engineering, it was about strategic understanding. In industrial warfare, the side that can produce more functioning weapons faster wins, regardless of whether those weapons represent optimal individual design. Adequacy at scale defeats perfection in small numbers. Manufacturing systems matter more than manufactured products. Japan had built beautiful tanks with precision transmissions that required skilled mechanics and careful maintenance. America had built adequate tanks with crude transmissions that could be repaired by semi-trained soldiers with standard tools. In the decisive test of combat across the Pacific, adequate at scale defeated beautiful in limited quantities. The Chiha's elegant transmission represented 2 decades of Japanese engineering excellence solving the wrong problem. The Sherman's crude transmission represented American engineering adequacy, solving the right problem. In war, solving the right problem adequately beats solving the wrong problem excellently. That truth was written in the technical reports filed by Jiro Sato and his team at Mitsubishi in the autumn of 1944. The captured transmission had revealed the fundamental flaw in Japanese military-industrial strategy. They had optimized for peacetime manufacturing excellence when they needed to optimize for wartime manufacturing capacity. They had pursued individual perfection when they needed systematic adequacy. They had designed transmissions that impressed engineers when they needed transmissions that kept tanks moving under combat conditions. By the time they understood these lessons, the war was already lost. The Sherman's crude gearbox had taught Japanese engineers truths about industrial warfare that should have been understood before the first shot was fired. Understanding came too late to change outcomes. The transmission sat silent in its test facility, a mechanical prophet that had delivered its message to an audience that could no longer act on the warnings. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.